So there's three main types of these things. It's solid, liquid, and hybrid. These ones are generally for
babies.
liquid rockets are often harder to store, launch, and make, but I'll show you that they can be simplified and understandable. So what even is a liquid rocket? Fuel plus oxidizer plus a spark equals
period that will have.
A liquid rocket combines liquid fuel with liquid oxidizer to burn violently and throw mass away from the rocket very quickly. The fuel stores the chemical energy and the oxidizer reacts with the fuel. After combustion, this creates hot, high-pressure gas that shoots out of the nozzle, producing thrust. We need this gas to exit the engine as fast, efficiently, and symmetrically as possible, bringing us to nozzle design. The hot gas is accelerated to Mach 1 with the converging section called the throat on the left. At this point, the speed is choked, meaning it cannot speed up without more surface area. On the right, the nozzle expands to increase the surface area, speeding it up further. The nozzle shape determines how much the exhaust expands before it leaves. If it underexpands, like the top picture, the exhaust pressure is still too high, so it keeps expanding after it leaves the nozzle. If it overexpands, like in the bottom picture, the exhaust pressure is too low, so the atmosphere pushes inward on it. Ideally, the exhaust is pressure matched, like in the middle picture, meaning its exit pressure is about the same as the surrounding air. The exit pressure depends on the ratio between the exit area and throw area, commonly called the expansion ratio. A bigger ratio lets the gas expand more, lowering its pressure and increasing its speed. The nozzle is curved instead of a straight cone, so it can turn the flow smoothly and keep it moving backward. Generally, a longer nozzle is more efficient at converting the exhaust velocity into thrust, but heavier. But how does fuel and oxidizer turn into hot gas? That brings us to the combustion chamber and the injector. The injector's job is to spew the fuel and oxidizer while also using the right ratio between both, atomizing the two liquids, mixing them quickly, and evenly distributing them. These are 4 different injector designs, each with their own pluses and minuses. Each balances pressure drop, mixing, stability, heat, and the ease of making it. Each injector converts pressure into fuel velocity, creating a pressure drop between the feed system and the combustion chamber. A higher pressure drop means more stability, but a harder working feed system.
There you go. Nobody works like David in this house.
You see all this red right here? It's very... This reaction starts in the combustion chamber, where an igniter lights the mixture of the fuel and oxidizer, releasing energy in the form of quickly expanding hot gas. But it's still very... Bonus! Let's cool it down. To prevent weakening or catastrophic failure, modern rockets use cooling systems. Warping, cracking, and melting all cause months of time loss. There are 3 main cooling methods. The first is film cooling. Film cooling works by injecting a thin layer of cooler propellant along the inside wall of the combustion chamber and the nozzle. That layer acts like a shield between the metal and the combustion gas. The second is ablative cooling, where a lining of material on the wall slowly chars away to protect the walls from heat. So the third method is regenerative cooling. It's one of the most widely used cooling methods in modern liquid rocket engines. This method runs the propellant through small channels inside of and around the walls of the rocket to absorb heat from the metal. It is then pushed back up to the injector. These cooling channels must balance space with pressure, as small channels have pressure loss while large channels may not move propellant fast enough to transfer heat effectively. What actually is the stuff spewing down and blowing up? Now let's talk about fuel and oxidizer. The OF ratio relates the mass flow rates of the fuel and oxidizer. This shows the content of the mixture in the combustion chamber. A common ratio is around 3.6, meaning 3.6 kilograms of oxidizer are used for every kilogram of fuel. Because this is a chemical reaction, there is a theoretically perfect ratio between the two, but real rocket engines don't run at that ratio. They often run fuel-rich, lowering the combustion temperature. In this graph relating the temperature to the mixture ratio, we see that the highest temperature is achieved close to the stoichiometric ratio. As it becomes more fuel-rich, the temperature decreases. Running oxidizer-rich is useful for different engine cycles. One example is the SpaceX Raptor engine that uses fuel-rich gas to drive the methane turbopump and oxidizer-rich gas to drive the oxygen turbopump. Many of these fuels and oxidizers are cryogenically frozen, meaning they're so cold that they stay liquid. Liquid oxygen is a common oxidizer that needs to be kept at minus 183 degrees C. As energy leaks into the tank over time, some of it turns back into a gas, creating a term called boil-off. Space taken up by boil-off in a tank is called the ullage. This is why a pressurization system has to add gas to keep the tank pressure from falling. Methods to control boil-off include venting, where excess gas is released, and thick insulation of the tank to decrease external energy. These things tend to go pretty high, requiring some force.
The moment you've been waiting for.
ISP is specific impulse. This is the propellant efficiency of the rocket, where F is the force in newtons, m dot is the mass flow rate of the propellants, and g is gravity. This represents how many seconds 1 kilogram of propellant can produce 1 kilogram of thrust. From this equation, we can find the force on the rocket by our engine. SpaceX Raptor has a specific impulse of 327 seconds, using liquid hydrogen as fuel and liquid oxygen as oxidizer. It pushes 717 kilograms of propellant through the exhaust each second. This means that the Raptor produces 2.3 million newtons of force max.
I mean, the first thing we should assume is that we are very dumb.